Hello fellow problem solvers. So today we're going to be doing a problem from the 1997 IMO, problem number 5. I suggest you try this problem out for a minimum of 15 minutes, ideally 45 to an hour, but not more than an hour and a half. If on the other hand you'd like to go along with us, I suggest you take 5 to 10 minutes to read the problem, see what it's about, get your first ideas out on paper, and then come back. So let's begin. So in summary, we just need to find all positive integers which satisfy this equation. So the question is, what are your first ideas when you see this equation? A to the power of b squared is equal to b to the power of a. Well, here, because we just have a on this side and b on this side and some exponents, and them being equal, it makes sense to look at the prime factorization of a and b. Namely, the first thing you may notice is that if some prime p divides a, that implies, because if p divides this side, it divides this side, it implies p divides b to the power of a, which implies that p divides b. And similarly, the other way around. So this means that a and b have the same prime factors. And now it makes sense to look at the exponents of those prime factors. So first let's write them up. Namely, ab equal to p1 to the alpha 1 times p2 to the alpha 2, so on and so forth till pn to the alpha n, and bb equal to p1 to the beta 1 times p2 to the beta 2 times all the way till pn to the beta n. Of course, this is assuming they have prime factors. If one of them is 1, then the other one is 1, and that's a solution. But looking at solutions other than 1, 1, assume they have prime factors and let the prime factors be this. So now a to the power of b squared is going to be p1 to the power of alpha 1 times b squared times p2 to the power of alpha 2 times b squared, and so on, alpha n times b squared. And b to the power of a is going to be p1 to the power of beta 1 times a times p2 to the power of beta 2 times a, and so on and so forth till pn to the power of beta n times a. Now, because these two numbers are equal, it must be that the exponents on these different primes must all be equal to one another, which means alpha 1 times b squared is equal to beta 1 times a, and also alpha 2 times b squared is beta 2 times a, and so on and so forth. So now what we have is, for each I, we have that alpha I times b squared is equal to beta I times a, which in turn means that alpha I over beta I is equal to a over b squared. Now, take 2 minutes to figure out what this means. For each I, 1 to n, we have alpha I over beta I is a over b. So this is the situation thus far. For all I from 1 to n, alpha I over beta I is a over b squared. Now the question was, what does this mean? Well, it means that this quantity right here, which is constant over the all i's, is either greater than 1 or it is less than 1. Now, if it is greater than 1, that means that alpha I is greater than beta I for all I, which in turn means that b divides a. On the other hand, if this quantity here is less than 1, then it means that beta I is greater than alpha I, which in turn means that a divides b. So now we have two cases, a divides b or b divides a. I invite you to pause for 5 minutes and try to solve one of the cases. Here's the first case I'll solve, a divides b. So if a divides b, what do we have? Well, this implies that a times c is equal to b for some integer c. And because a and b are positive integers, that means c is a positive integer as well. Now, plugging this back into the original, we get that from a to the power of b squared is equal to b to the power of a. We get that a to the power of ac squared is equal to ac to the power of a. Now what you can do here to solve this algebraically is just take the 8th root of both sides, and what that gives you is a to the power of ac squared is equal to ac. We can further simplifying this by dividing a on both sides, and what we get is that a to the power of ac squared minus 1 is equal to c. Now, what would you do with this? I invite you to pause for 2 minutes and see, can you solve this equation in the positive integers? Now, what I see immediately here is that if c is 1, that means a is 1, but we're not looking for those solutions anymore. On the other hand, if c is, say, 2, for c2, we would have a to the power of 4a minus 1 be equal to 2, which forces a to be 2, and then this whole thing becomes 2 to the power of 7th, which is a lot bigger than 2. I mean, a lot is subjective, but if c is 3, we would get like 3 on one side, and then a to power of 9a minus 1 needs to be equal to 3. And here we get at minimum a number of the form 2 to the 17th, which is a lot bigger than 3. So the intuition from these couple of cases starts piling up, and the intuition is we can say that 2 to the power of 2c squared minus 1 is going to be greater than c. Now, the easiest way to prove this is via induction. Namely, for c equals 2 and 3, we've already proved the claim. Assume the claim is true for some c, and now for c plus 1, we would have 2 to the power of 2c plus 1 squared minus 1, which would be equal to 2 to the power of 2c squared minus 1, because we want to use the inductive hypothesis, times whatever is left, and what is left is 4c plus 2. And now, this thing right here is greater than c, and 2 to the power of 4c plus 2 is greater than 2 to the power of 2, which is equal to 4c, which is greater than c plus 1, for c greater than 1/3. And now we're done. We have proved that this whole thing is greater than c, and this thing is less than or equal to a to the power of ac squared minus 1. So this case, a dividing b, does not work out. So for the other case, I invite you to pause for 3 to 5 minutes and try to solve it, or at least play around with it for a bit and see how far you can push it. So now let's go to the next case. Case 2, b divides a. We have ab squared is equal to b to the power of a. So now from b divides a, what we can say is there exists a c such that bc is equal to a. So what does this transform into then? Well, a is bc, so we have bc to the power of b squared is equal to b to the power of bc. Taking the bth root of both sides, this transforms into bc to the power of b is equal to b to the power of c. And now from here, we divide both sides by b to the power of b. And what we get is that c to the power of b is equal to b to the power of c minus b. So now I invite you, if you haven't already, pause for 5 minutes and try to solve this case. Well, there's a little bit of a deja vu in this case now, isn't there? Because it's quite similar to the thing we had before. Let's just look at the exponents. C and b must have the same prime factors, so let c be equal to p1 to the gamma 1 times p2 to the power of gamma 2 times all the way till pn to the gamma n. And now we know that b is equal to p1 to the beta 1 times p2 to the beta 2 and so on till pn to the beta n. And now this thing right here gives us that b times gamma 1 is equal to c minus b times beta 1. Now this of course holds true for all I, so now we have this. In other words, similar to what we've done before, gamma I over beta I is equal to c minus b over b. Now this can either be less than or equal to 1 or greater than or equal to 1. Now we can just do the two cases. Namely, if this thing here is greater than or equal to 1, then we have gamma I is greater than or equal to beta I for all I. And what this case gives us is, because gamma I is greater than or equal to beta I, this means that, in fact, b divides c. We got this from assuming that c minus b over b is greater than or equal to 1, which means that c minus b is greater than or equal to b, which means that c is greater than or equal to 2b. So everything checks out. Now let's put b times d is equal to c and plug it back into the original equation. So what do we get? Well, c to the power of b becomes bd to the power of b is equal to b to the power of bd minus b. Now what we can do is rewrite this, and then we take the bth root of both sides, which gives us bd is equal to b to the power of d minus 1. Dividing by b on both sides, we get that d is equal to b to the power of d minus 2. Now, pause for 1 minute and ask yourself, how do you solve this equation? Well, you ain't got much here. The only thing you can really do is check cases, namely for d equals 1, we get 1 is equal to 1, but we're not looking for those solutions. For d equals 2, we get 2 is equal to b to the power of 0, which means nothing to us, that's 1, so we get a contradiction straight away. For d equals 3, we get 3 is equal to b, which then implies that c is equal to 9, which implies that a is equal to 27. So we get a new solution, ab being 27 and 3. Then we move on to d is equal to 4. And what we get here is that 4 is equal to b squared, which immediately implies b is equal to 2. These two imply that c is equal to 8. And then we have a is equal to 16, which gives us another solution, namely ab is 16 and 2. And now let's look at d is equal to 5. We'll get 5 is equal to b to the power of 3, and this does not have a solution. And what we can already see is this is greater than or equal to 2 to the power of 3, which is 8. So as it was in the other case, it seems like we might be reaching the end of our solutions. This right here might grow way too fast, meaning that b to the power of d minus 2 might grow a lot faster than d. So let's try and prove that now. Again, the most natural way to do this is via induction. So for d equals 5, this is true. Let's assume it's true for some d, that 2 to the power of d minus 2 is greater than some d. Then what do we have for d plus 1? Well, 2 to the power of d plus 1 minus 2 is equal to 2 times 2 to the power of d minus 2. And this is by the inductive hypothesis, greater than 2 times d. And then this is greater than d plus 1 because d is greater than 1. It's at least 5, which means that 2 to the power of d minus 2 is greater than d for all d greater than or equal to 5. Now this means that b to the power of d minus 2, and b is at least 2 if it has a solution, is greater than or equal to 2 to the power of d minus 2, which is greater than d for d greater than or equal to 5. So now that we found all the solutions in this subcase, let's move on to the other subcase. So now that we've solved the subcase, gamma I is greater than beta I, which implied that b divides c, we have the opposite case, namely where c divides b. However, take a minute and see what happens with this case. Well, what happens is, if c divides b, that means c is less than or equal to b. And here this was all predicated on the fact that gamma I is less than or equal to beta I, which stemmed from the fact that c minus b over b was less than or equal to 1. However, if c is less than or equal to b, then this thing right here is negative, so this holds up. But what we get from our problem statement, namely that c to the power of b is equal to b to the power of c minus b, when we have c dividing b, then cd is equal to b for some d, and plugging that in here, we get c to the power of cd is cd to the power of c times 1 minus d. And now when we take the c throughs of both sides, we get c to the power of d is going to be equal to cd to 1 minus d, which is equal to 1 over cd to the power of d minus 1. And now if we multiply both sides by cd to the power of d minus 1, we get that c to the power of 2d minus 1 times d to the power of d minus 1 is equal to 1, which makes both c and d equal to 1, which implies b is 1, which implies a is 1, and so this case is done. Now let's bring it all together, summarize it, and write up a solution. So we are first given this problem, and then we say, note that a, b, being 1, 1, 27, 3, and 16, 2 are solutions. And now we are going to be looking for solutions different from these. So the first thing we notice is, if a is 1, that implies b is 1, and if b is 1, that implies that a is 1. So now assume that neither are 1, which means that both can be written as products of prime numbers. And because if p divides a, it follows that p divides b to the power of a, which implies that p divides b, and vice versa. If p divides b, it follows that p divides a to the power of b squared, which implies p divides a. Now this means a and b share the same prime factors, which means we can factor them like this, with the same prime factors, p1 through pn, but having potentially different powers. So now if we look at the equation a to the power of b squared in terms of these powers of these primes, what we get is that for each I, we have pi to the alpha I times b squared is going to have to equal pi to the power of beta I times a, which implies that alpha I times b squared is beta I times a for all I. And now from here, what we can say is that alpha I over beta I is going to equal a over b squared. And now we break this up into two subcases. Either a is greater than or equal to b squared, or b squared is greater than a. In the first case, this implies that a over b squared is greater than 1, which implies, because this is equal to ai over bi, this implies that ai is greater than or equal to bi for each I, which means, because these are the prime factorizations of a and b, that b divides a. Now what this tells us is there exists a c such that b times c is equal to a. And now we plug that back into the original and we get bc to the power of b squared is equal to b to the power of bc. We take the bth root of both sides, and what we get is bc to the power of b is equal to b to the power of c. And now we can divide both sides by b to the power of b. And what that gives us is c to the power of b is equal to b to the power of c minus b. And now a little bit of deja vu tells us that if c is equal to p1 to the gamma 1 times all the way till pn to the gamma n, what we'll have for each I is that gamma I times b is equal to c minus b times beta I, which implies that gamma I over beta I is equal to c minus b over b. Now this implies that either this is greater than or equal to 1 or less than or equal to 1, which implies either b divides c or c divides b. However, and this time we're going to use a little trick from before, notice that when a is greater than or equal to b squared and a is equal to b times c, this implies that c is greater than or equal to b. So because c is greater than or equal to b, that means that we only need to pay attention to the case b divides c. And in this case, that means that beta I is less than or equal to gamma I for each I, which here would mean that c minus b over b is greater than or equal to 1, which means that c is greater than or equal to 2b. So now that we know that b divides c, let's write c as b times d, and then plug that back into the original. And what we get from here is bd to the power of b is equal to b to the power of b times d minus 1. Take the bth root, we have bd is equal to b to the power of d minus 1, divide by b, and you get d is equal to b to the power of d minus 2. And now we solve this case, and we do that. We have this case. So we first proved that for d greater than or equal to 5, this is true by induction. For d equals 5, it's true. We have 2 to the power of 3, which is 8 is greater than 5. And then assume it is true for some d. And then for d plus 1, we have 2 to the power of d plus 1 minus 2 is equal to 2 to the power of d minus 2 times 2. Applying the inductive hypothesis, this is greater than d times 2. And because d is greater than or equal to 5, this is greater than d plus 1. Now this means here that we only have to really worry about cases for d being less than or equal to 4. And what we get is d is equal to 4 implies b is 2, d is 3 implies b is 3, d is equal to 2, 1, 0 implies no solution. And for these two cases, this implies that c is 8, c is 9, and then a is 16 or a is 27, which gives us the 2 out of our 3 solutions. And now we go back to the other case. So this case gave us our 2 solutions, namely AB 27.3 and 16.2. And now with this case, we have that alpha I over beta I is equal to a over b squared, which is less than 1, which implies that alpha I is less than beta I, which implies that a divides b. And now here we do write b in terms of ac as before, and then this transforms into a to the power of a times c squared minus 1 is equal to c. And then we show via induction that if c is greater than 1, we know a needs to be greater than or equal to 2. And now via induction, we show that 2 to the power of 2c squared minus 1 is greater than c for all c greater than or equal to 2. Our base case is 2 to the 7th is greater than 2, which is very true. And then assume, and what we have to prove is 2 to the power of 2 to the c plus 1 squared minus 1 is greater than c plus 1, which we just did. Now this shows that this case has no solutions, and that the only solutions are the ones that we've found thus far, which are AB being 1, 1, 27, 3, and 16, 2. And as always, thanks for problem solving.